Unit 4, Lesson 9. Unit 4, Lesson 9. Okay, so in this lesson, we're going to investigate the graphs of polynomial functions which have zeros with the multiplicities greater than 3. Okay, so we're talking about different multiplicities of, so we talked about up to 3 yesterday. Remember, and 3 is where that point of inflection happened, that weird thing where it shifts from concave up to concave down. So it kind of twists. So we're going to look and see what happens for these ones. So x minus 2 cubed versus x minus 2 to the 5th versus x minus 2 to the 7th. So for those of you who are gone, x minus 2 cubed is a multiplicity of 3. That means that's happening 3 times, right? If I wrote these factors out, there'd be 3 of them. So that means that that 0 is happening 3 times, but we don't count that 0 3 times. It's not intersecting through there 3 times. It's either bouncing or has something happening there. And so we got to kind of figure that out. So let's see what's happening here. So go ahead, why don't you guys get your calculators out real quick. Go ahead and put these in, y1, y2, y3, and kind of look at how they change. Okay, I'll go ahead and do that with you here. So if we go here, let's go y equals, we got x minus 2 cubed. Okay, let's see what that looks like. Okay, let's go ahead and, let's see here. Let's go ahead and change my window a bit. Oh, no, window is good. Okay. I think I'm going to make it actually negative 10 to 10. Let's make it a little tighter. And then we can go by that. Yeah, that's a little better. Okay, so there's what the first one looks like with multiplicity of 3. Okay, let's go down here. Let's try it with multiplicity of 5. Okay, so it got a little bit steeper. Okay, got a little bit steeper. And if we try the multiplicity of 7, right, and then steeper. So then let's just think about, why is it getting steeper? Yeah, you can say a stretch, but one thing stands out to me pretty big is that as I do a multiplicity, if you think about foiling that out, for sure what's going to change is that n number, right? That y-intercept number. So if I do cubed, what's the y-intercept going to be? Not 6. You're just doing a silly mistake. 8. Negative 2 cubed, right? Not 3 times 2. So if my y-intercept for this one is negative 8. And it stays negative, right? Negative 2 times negative 2 times negative 2. So that's 3 negatives. So with a 5, it's going to be, what's 2 to the 5th? Right. And then this one's going to be negative 128. So that's one reason it's getting steeper, because the y-intercept's getting longer, like it's getting deeper, right? So that's one thing to look at. Our x-intercept's the same. They're all going through 2. You guys see that? Okay, every time. So if we just kind of drew these, negative 8, so the first one's going to go something like this. And then the second one through 32, 10, 20, 30, 40, 50. So 30, it's going to be more like this. And then the one's way down here, it's like at 128, so it's going to be kind of, we only see the cross like that. So you can see as the multiplicity gets higher, it gets steeper, and the y-intercept's one reason, but also just it's getting steeper in the sense of the number of times it happens. Okay, and it says what happens if the multiplicity of the 0 increases through the odd numbers? The graphs still have the inflection, so it's harder to see as it gets steeper, but they still all switch, like we talked about yesterday, to concave down to concave up. So these are all still points of inflection. Whoops. Just inflection. Okay. Points of inflection, and they're all happening at 2, 0. So this is a good review for those of you on yesterday. We noticed with the odd at 3, when things went through with an odd multiplicity, they switched from, it's like an easier picture to see. Like if I said this is a 0 right here, they switch from, like this is concave down, we call it, because it's shaped down. And this right here is concave up, and so they flip their curvature. So this goes from concave down to concave up. And the other way you could do it is if you went concave up to concave down. And they would switch the curvature that direction. Okay, so just keeping that stuff in mind. Okay, any questions? Any people got gone yesterday? Points of inflection. So it just switches the curve.
Is that what inflection means?
Yeah, points of inflection. That's what it means. At a point of inflection, it switches the curvature.
You said like the multiplicities.
Yep.
So like the 3 bounces twice, you say?
The 2.
The 2 bounces.
The 2 is the same 0 twice, and it reflects off. It bounces off of it with the 2. With even. So with odds, we're seeing that they have a point of inflection. Okay, so at 3 is the point of inflection where it still goes through. Now think about why. We talked about this yesterday, and Stephanie Rapp is like, oh my gosh, I just memorized it. That's crazy because she took this class last year. But the point is that why does the odds go through and change the point of inflection versus the even? Why do you think that happens? What's that? Close. Yeah, who said that? Because the negatives. Odds can have negatives. So it's going to go through because it can go down there. The evens can't. So it's going to go whoops, and it's going to go back to positive. Right? Because when you have an even polynomial, it's not going to have negative issues. When you have an, or not, sorry, it's not going to be negative because everything negative times negative is going to be positive. So evens bounce, odds go through because they can be negative. Okay? So that's the idea. Okay, so graph the following on the grid. So now let's look at the square ones. Let's do the same exact thing. I'll go to my calculator. We'll just go and change them. Just go up there and change your exponents to 2, 4, 6. What's that, Aiden? Sorry for your loss. 4 and 6. Okay. Now look, none of those what? None of them went down. There's nothing down here. 2, 4, 6. So here's your 2, I think. 4 and 6. Same thing applies. They got steeper, right? Because their y-intercepts are still going to get bigger, right? And their y-intercepts are just going to be positive, and so that's why they're all up. Because you have 2 squared, 4. So the first y-intercept's at 4. The reason you're saying that doesn't look like 4, well, because my scale is 120. Okay? This one right here, this one right there. So they're just growing that way. So you can see of this one, they're all up. So we got this one's wider. That's the first one. Okay, and the second one goes, so we have 2 squared, that's 4. 2 squared to the 4th, that's, what is that, 32? No? 32? Yeah. No, 16. 16, and then 64. So then we have here, and then we have 64 is going to be here. So this is line 2, line 3. Okay. And so what happens, and this is the other thing we learned from yesterday, the bounce point, or these even points, is called tangent, because it hits it one time. So these tangent at 2, 0. So when things bounce, we say tangent. When things twist through, we say point of inflection. Okay? We expect tangent with evens. We expect point of inflections with odds. Okay? All right, cool. Any questions on those? Pretty good? Okay, let's go ahead and go through this here. So even odd multiplicity is 0. A zero of even multiplicity, 2, 4, 6, 8, occurs where a graph is tangent to the x-axis. So that's an every time thing. Okay? Every 2, 4, 6, 8 for that multiplicity will provide a tangent point. What's a tangent point? A bounce point. It's going to come and hit it and come down. For those of you guys who've gone yesterday, well, that's right here. See this right here? That's a tangent point. It's hitting it and bouncing back. So the tangent point's not just for a single graph. It can be parts of a graph. So one factor of a graph can have a tangent point. Okay, so right here I got a tangent point. Right here's a what? Definitely a, yeah, that's a point of inflection point right there. Good. Okay, so then we got, that's a regular, so I'd say that's a 1. I don't see any change in point of inflection, right? It's going straight through. So the 1's kind of the exception. When it goes straight through, that's just going to be a single factor. Okay, and then here, that's going to be that looks like it's tangent and then really wide. I'll have to see what's going on here. I'll have to zoom that in a little bit. I don't know if it's, because it is switching concavity, see that? So yeah, that might be tangent, just one tangent, and then another one. So that could be multiplicity of 1, multiplicity of 2, multiplicity of 3, or sorry, 1. Looking at this graph here for part 2, just another thing you can do is count the change of direction. 1, 2, 3. So we're expecting maybe a degree of 4. Okay, I need to investigate this little valley here. It's concerning me, but just first look, I could think 4. This one, 1, 2, 3. So 3 could be, so that's going to be probably a 4 as well, because it definitely twists. So we're going to have something to look at there. But anyway, all right, so real zero of odds is always going to be your point of inflection. The sum and multiplicity of zeros will be the degree of the function. Okay, so all these are kind of the for sure's. Okay. All right, so looking at these 4, what's it say to do with the graphs below are screenshots from a graphing calculator? Well, thank you for that. Okay, and then it says, in each case, state the number of distinct zeros and the possible multiplicities. So this is good, possible. Okay, so let's just do these all right on the graph for mine. Okay, how many distinct zeros do you see? So distinct means different. That doesn't mean what degree, right? Because you can have a multiplicity of 2, which is the same 0 twice. So that's just that 1 0. So like right here, that bounce, that's worth 2, isn't it? Okay, so in terms of the bounce multiplicities, but it's only 1 0. So back to my original question, I'm starting to ramble a little bit. Part 1, how many distinct zeros do you see? 2, that's it, right? There's just 2, no, you have to look at the x-axis. There's this spot and this spot. Okay, so first for number 1, 2 distinct zeros. Okay. How many zeros do you see that is an even multiplicity? 1. This bounce guy, right? So 1, 2, 4, or 6 multiplicity, like etc. Even. You can say 1 even multiplicity is fine. And then the third one, or the other one, excuse me, is a odd, right? 1 odd multiplicity. Three, 5, 7. Yeah. Okay, how about part 2? How many zeros do you see? Yeah, part 2. 3. 1, 2, 3. So they went ahead, like they said, make an educated guess. So I told you this is kind of concerning. They're counting that as 1, 2, 3. So 3 distinct zeros. Okay. What type of multiplicity do you think this one is? 1. Right, that's 1. And that's 1. So we're going to call these 2 real zeros of 1. Because 1's different than 3, 5, 7. Do we understand that? How do you tell the difference? Here, it changes concavity. Here, it doesn't. That's how you can, this one versus this one, you can see the difference between the 1 versus the 3, 5, 7s. Okay? For which one? Right here? 1. So there's no point of inflection, so it's just a 1. So when I say odd, Aiden, so this is kind of not 1, though. We're not talking about 1. We're talking about 3, 5, and 7, okay, for labeling. Okay, so there's 2 real zeros of 1, okay? So that means it goes straight through. So this one goes straight through, this one goes straight through. Again, what I mean by straight through is there's no point of inflection. It's not switching on us at all. Okay, there's no turn. And then we have 1 of a what? E, 1 even, good. Okay, how many distinct zeros are on part 3? Good, 1, 2, 3. Okay, how many even? 2. I put 2 even 0 multiplicities. Okay, and then is that last one a odd 3, 5, 7 or a 1? It's a 1. Goes straight through. Okay, good. And the last one. How many zeros in the last one? 3 again. Good. Okay. See here. Looks like, again, what are these two? 2, yeah, real zeros of 1. Good. 2 real zeros of 1. And the last one is a odd. 1 odd multiplicity of 3, 5, 7. Okay. All right, so which of these 4, could represent a degree of 8? Which of these could represent a degree of 8? So a way you can do this is those 1s are 1s, right? So get those first and then see what possibilities you have. So for example, this is a 1. Or sorry, this is a 2. And what's this? Has to be 3, 5, 7, right? Is there any way I can add a 2 or 4 or a 3, 5, 7 to get 8? What's that? What? Ah, yeah, see? You got it. Okay? So 2 plus 5 is 7. 3 plus 6 is 9. Like, none of those are going to work. You can't get 8. So number 1's not good. You see what I'm saying? I'm looking at integers here. So this here is a 1 and a 1. So I know it's 2 plus, what's this one? That's an even, right? So that's 2 plus an even number. I can get 8 now. This could be 1 plus, that's 2 plus 6. If this is a 6 here, which it could be. So it's this one. That one could be possibly 8. We'll talk about the other two, why they're not, in a second. But that's integers. Okay, that's thinking about what you can add. Okay. So this one, that's 2, 4, 6, 8. 2, 4, 6, 8, and a 1. That one messes us up. And go 2 plus 4 is 6 plus 1. Can't do it, right? So those, I can't get that one added to 8. The last one is a 1 and a 1 and then an odd. So it's 2 plus an odd. 2 plus 5, 7. 2 plus 7, 9. I missed the 8. I can't get 8 there either. Okay, we good? Okay, part C, in which the graph is a leading coefficient positive. So we know this in terms of, remember, if your parabola, or that cubic, if it's falling versus rising, how it ends, can tell you if it's positive or not. So they're telling us that 3 and 4 are positive. That's what they're saying, 3 and 4. Okay, good. So why is 3 and 4 positive? Can you see it? Yep, the change. Good job, Keegan. It rises and rises, right? Rises, rises. So those ones can be positive. These ones fall and fall, so that means it's negative even. Like think about a parabola where it falls on both sides, right? That'd be a negative one. And this one here falls and falls. Okay, so these two would be your example of positive coefficients. Okay, very good. All right, almost there. Okay, so let's look at this one. Without using a graph calculator, make a rough sketch of this graph. Okay, so we have one thing to point out. We have 1, 2, 3 zeros, right? Not 2. So right now we'll just make a dot at. Let's make a dot at 0. Make a dot at 1 and 2, 3, 4. So we know it's going to go through those spots. It's negative, so it's going to be falling. Okay, it's going to be falling like it's going to be coming from the bottom. Excuse me, like a parabola. Think like parabolas. If it's negative, it's coming from this way. We do have a 6 in terms of total degree. Okay, so what's going to happen is it's going to come up through here, and then it's going to come down. And what's it going to do at that spot? It's going to bounce. Okay, it's going to go bounce off of that, and then it's going to come back off of here, and then what's it going to do through the last part? Straight through. Okay, look at that, looks negative, right? Down, down on both sides. Okay, that's how you can account for the negative. If that wasn't a negative in front, it'd be coming from the top. So it would go back down and then back through. Okay. You guys verify with your calculator, but I won't do that one for this time.
So if the start comes from the bottom, then that means the front is negative, and if the back, that means the back is negative? Or like the constant?
So if it's even, which this one is, it should start and end the same.
Okay.
Does that make sense?
Yeah.
So if this was a, let's say that if I threw another x and you made it a 7, and then this ended up, then it could be positive, because it's coming from here, and so it's going in a positive direction. Does that make sense?
Yeah.
But if I don't have an x here, and this is even, this is falling, that's negative. So if it's even and then flipped, so I think if we just made a positive x, let me just kind of see if I can figure out what this would look like. So if this is a positive x, it should come down here, bounce like that, if it was positive. It'd be finishing up and up. Okay. Right. Yep. Because no matter what, when I multiply all these x's, if I FOIL this out, I'm going to have a negative x squared. So that negative is going to carry through. Okay. All right, good. And then another thing to think about with that is, notice, here's an interesting thing. That one is, I just erased it, sorry. But did you guys see how this is a negative graph, but negative 1⁴ is positive 1, right? Times a negative 4. So where was our y-intercept on that graph? So -1, so the one we just did was 0. Let me see here. 1 times -4, it should be at -4. What do we have? Oh, yeah, it's 0, sorry. Because the y-intercept, because if you put 0 in for x, the whole thing's 0.
Okay.
Yeah, sorry, I was overthinking that one. Yeah, never mind, we're good. All right, let's look at these two. The following graphs represent the polynomial function p of x to the lowest possible degree. In each case, state the degree of the polynomial function. For p of x of 0, state the points of the graph which represent real and equal roots. So this is just telling you your intercepts, your roots and zeros. All right, so state the degree. So the degree, so I got 1 turn, 2 turns, 3 turns. So I'm thinking that one's probably a what? Degree of 4. Okay. You can also see right here, this is a multiplicity of 2, 1, and 1, right? So it's 2 plus 1 plus 1. So you have 4 is the degree we're expecting. State the points. So the points.
You said 2 because it's the lowest possible degree?
Yes. For what do you mean by lowest possible? Sorry. Yes. Yes.
It could be a
right.
positive.
Correct. This technically could be a 4 or 6, but we don't know. Yes. So they're just saying just take the 2 or. So we're going to do 1, 2, or 3. Okay. And so then your zeros are A, D, and F, right? And so it says, state the points on the graph which represent real and equal roots. So A, real and equal. Okay, so A is only real and equal, right? Real and equal means what? The bouncers, because they have two answers, like the same answer twice. That's what the real and equal part means. So like, if this was a -3, it'd be x plus 3 squared, which means -3 happens twice, but we only count it once, but it's equal. That's what this means. Okay, last one. So this one's a 3 for sure, right? You see it twist. And this is also a 3. So 3 plus 3, degree is 6. Okay, and then it says real and equal, there is none, right? For the real and equal, hold on. So the points of the graph were real and equal roots. If they're saying real and equal, then this one would technically be none, but they're saying P and S. Real and equals, but those are odd. Oh, yeah, that's stupid. Sorry. Dumb. It is P and S. It's P and S because this could be 3 of it, right? So 3 equal. I'm just only thinking 2. So they're saying is anything over happening once is they're going to have equal solutions. So this is, again, if I just said that this guy right here was -2 and this was +2, these multiplicities say it has to at least be this and this, which means they happen 3 times. So they're still equal. It's above 2. My bad. Okay, so I know it's confusing, part 2, but part 2 is saying state the points of the graph which represent real and equal roots. So it's essentially saying which points in the graph are a multiplicity bigger than 1. So they're a bigger multiplicity than the 1. That means they happen more than once. These two only happen once, so those aren't equal roots. They only happen once. This happens twice, so 2 equal. This happens 3 times at least, so 3 equal, 3 equal. So they're all bigger than 1. That's the question. Okay? All right, let's look at this other one here, and then we'll talk about the extension just a little bit. On the grid, sketch a graph of the polynomial for the following conditions. Okay, so we'll sketch these. Positive leading coefficient. Okay, 1 real 0, multiplicity 1, 2 real zeros, multiplicity of 2, and 1 real 0, multiplicity of 5. Okay, so this is possible. So you can kind of do a lot of different things here. Okay, we know if their multiplicities are 1, 2, and 5, then it's going to be, what's my degree? 8. So that means my start behavior, my end behavior will be the same, right? When you have even, it's going to start and end the same. So positive leading coefficient, so that means I'm thinking it's going to look something like this. Obviously, it's going to have some shifts, but its end behavior is going to be up and up. Okay?
If it wasn't 8, like if it was 7, it would be up and down?
Right. Odds, because cubic, think about cubic, right? Cubics do this.
But then the positive leading coefficient, does that just mean that the start will be?
Right. That's think like a parabola. The parabola, that's a positive parabola, right?
Yeah.
So this is going to start and finish. Like this, the ends are going to look like this.
That's because of the positive
Right.
coefficient?
Yep.
But if there's a positive leading coefficient at 7?
Then it would start positive. It would start negative and come up. Because when you have a negative x, that to an odd is a negative number. So like, just think about this here. You're asking great questions. So if I had x cubed, right, and you said if it's positive, so if I put a -2 in there, so that's -8, I get -16, so I'm down here. So it's coming from here. Do you see what I'm saying? Okay. She's just asking about the end behavior. So if that was confusing for you, just think about how it starts. Guys, in the end game, if you have the equation, you can always see how it starts. You can plug in a point and see if it's low or high. Okay? But anyways, this one here, what we've decided, it's even because 1 + 2 + 5 is 8. Okay? Positive, that means it's going to come from here. So let's get our zeros. We have 1 real 0. Let's do this one. Let's do 2 real zeros, multiplicity of 2. So that means here and here, I guess. And then 1 real 0, multiplicity of 5. Okay? So that means, like, if it's a multiplicity of 1, that means the first one we can just say, and they don't have to be in this order. They just went the order they told you. That means it goes straight through, right? No concave switch. 2 real zeros, a multiplicity of 2. That means twice it's going to what? Bounce or be tangent. So it's going to come up here, come down, and come up here, and then bounce and come down here. So I have like 3 little loops. So bounce twice. And the last 0, it's going to do the twist. So I'm a little too wide here. Let me fix that. Let's go a little bit tighter. So it's here, here, and then here, and then it's going to turn from concave up to concave down and then finish out. I've exaggerated there, but so you can see the turn. Does So that would be an example of a possible solution. So you guys could have different graphs. The order could be different, but that's an example of doing what they asked. So then to what Cassie was saying, see, I finish up, or start up, finish up. Okay, that's how evens are going to be. Evens are going to match each other because evens are symmetric in the sense of their finish. Okay, so let's look at this one, negatively in coefficient. And now we have 1, 3, and 4. So we're at 8 again, so this is even again. So they're going to finish the same. So for this one, wait, negative 1 real 0, oh, no, 2 real zeros. 1, 2. Yeah, so actually we added this one wrong. This is 1, 2, 2, 5. It's 10, not 8, because this happens twice. But still even. Right. We drew it right. Just it's actually a 10. Okay, because 1 real 0 multiplicity 1, so that's a 1. 2 at 2, so that's 2 and 2. And then 1 at 5. Then you add that for your degree. So then over here, 2 at 1, so that's 1 and 1. 1 at 3, 1 at 4. So 4 plus 3 plus 1 plus 1 is 9. So it's going to be odd. It's going to finish differently. So that means for odd, I told when Cassie's asking, I said your regular odd that's positive starts low and comes high, right? But this is an odd that's starting negative. So it's going to start high and go low. Right? And that makes sense. You think about it, if it's negative, it's coming here, and it's going to finish down here. It's getting worse. That's if it's even. Evens finish the same. Odds don't. This is odd. Yeah. Okay, so just think, Aiden. Here's a normal cubic graph looks like this. It starts negative, finishes positive. That's a positive cube graph. A negative cube graph does this. So we have this type of finish because we have an odd and it's negative.
But when it starts from down low and also.
But that's an even. You're saying they're starting and ending the same. That's this. So that would be this. If this is negative, that's what that would do. That would start low and finish low. Remember, if it's even, they're going to finish and start the same. If it's odd, it's going to start one way, finish the other. Okay, that's the big thing you need to get down. Okay, 2 real zeros, a multiplicity of 1. So then we have two things going through once. Okay, so we'll do a dot here, a dot here. We have 1 real 0, multiplicity of 3. We got a twist there. And then 1 with a multiplicity of 4, we got a bounce there. Okay, so we are going to start high. We're going to come down, go through, and then we're going to concave down to concave up. Got a twist right here. Okay, and then a bounce. And see how it forces me to do what I'm supposed to do if you follow your multiplicities. You knew that last one was a bounce. That's why I got back down there. Okay, so we started high, we finished low. Okay, that's a negative odd look. Okay, any questions on that? All right.
You don't have to do it in that order, right? Because you have your bounce first and then your twist?
Yes, your order doesn't matter. Yeah, order doesn't matter. It's like multiplication, right? You can flip things. So your graph, you can do it however you wanted. Let's just, if you wanted, like, yeah, you could have, let's just do a different color real quick here. So if let's say I do my bounce first. So bounce, let's say it bounced here. Then we went 1 through here. Say we twisted here, and then 1 through here. See, it still finishes the same. So any way you want to do your pattern, you're still going to start and finish the same behavior. Yep.
How do you, in this one, how do you know the difference between your...
We're going to stop there for the video.